In this video, we'll see how to use a computer to generate a string of numbers, or sequence, that can serve as a model of random variables. Our principal target will be the uniform 0-1 distribution. A random variable that comes from this distribution is continuous. Its probability density function f of x takes a value of 1 whenever x lies strictly between 0 and 1, and takes a value of 0 otherwise. The graph of this probability density function is easy to sketch. It's simply a horizontal line at height 1 that extends from x is equal to 0 to x is equal to 1. Of course, it hugs the horizontal axis everywhere else. We want to generate a string of numbers, each of which looks like it came from the uniform 0-1 distribution. We also want the numbers to look like they're independent of one another, but for our purposes, independence will be taken as a given. We're going to pull this off using an affine linear recursion. U sub t is equal to a times u sub t minus 1 plus b. We'll set u naught equal to c and iterate forward in t from there. Importantly, we'll choose the constant a to be positive and the constants b and c to be non-negative. We'll also choose them in a way that ensures the numbers we generate are integers. With certain choices of constants a, b, and c, the iterates we generate will tend to grow without bound. To keep some control on this growth, we turn to modular equivalence. This sounds technical, but it's the same sort of thing you do when you identify the same positioning of the hands of a clock with two different points in a day. The main difference here is that rather than basing an equivalence on the integer 12, we'll use an arbitrary integer m, called the modulus. We say two integers are equivalent mod m if they leave the same remainder when divided by m. So for example, the integers 4 and 7 are equivalent mod 3 because both yield a remainder of 1 when divided by 3. To emphasize our use of mod equivalence, we'll rewrite the recursion like this. Now, luckily, you don't have to strain your brain to iterate this beast if you're willing to use a computer. For instance, the mod function in Excel will automatically wrap the sequence you generate around a clock with m hours, so to speak. Let's look at an example using the following choices for a, b, c, and m. I've set things up here in Excel. I've put the constant a in cell A1, the constant b in cell B1, and the constant c in cell C1. To iterate the affine linear recursion with modular wrapping, I'll now write mod $a$1 times cell C1 plus $b$1. I need a comma, and I'll add 2 raised to the power 32, which is our choice for the modulus m. I'm using dollar signs here to lock in the cell name for the constants so we can copy the formula easily. When I press enter, I get my first iterate, 82,941,952. I can generate a string of iterates just by copying the formula like this. Notice that these iterates don't match our target. Uniform 0-1 variables should fall inside the unit interval. We can fix this simply by dividing the numbers in column C by the modulus m. This gives us the sequence of numbers between 0 and 1 you now see in column D. If I iterate much further in time and tally up the results, we can see a nice match between our computer work and the probability density function of the uniform 0-1 random variable. Here's the result of my tally of 10,000 iterates, or what some might call pseudo-random numbers. There's a lot going on here, so let me go through things systematically. I started off by dividing the unit interval into 20 subintervals of equal width. I then went through my list of 10,000 iterates and placed them in the appropriate subinterval. This allowed me to count how many iterates fell into each of the 20 subintervals. I then converted each of these 20 counts into densities by dividing them by the product of 10,000 and the subinterval width. This plot shows the densities that I calculated as horizontal lines above the corresponding subinterval. As you can see, the result is a step-like graph indicated in black. Superimposed on this is a dashed purple line that corresponds to the graph of the probability density function of the uniform 0,1 random variable. We can see pretty close agreement between the densities observed in our computer calculations and the true density. It's close enough for me to be satisfied with the computer-generated numbers as a suitable model of uniform 0,1 random variables. Now, as I said earlier, we're also treating each of our iterates as a random variable or random number that's independent of others in the same list. While independence can be explored and even challenged, we'll just take it for granted and move on. In a way, the ability to generate random variables from a uniform 0,1 distribution is a mathematical superpower because the numbers we generate can be transformed into ones that model any distribution that might interest you. Take, for instance, the continuous random variable whose probability density function looks like this. We can turn a sequence of numbers that model independent uniform 0,1 random variables into a new sequence of independent random variables for whom this triangular graph is the probability density function. We do this by carrying out the following steps. The first step is to establish the cumulative distribution function. As we had seen in a previous video, the cumulative distribution function associated with the probability density function here looks like this. We then determine the inverse of the cumulative distribution function, at least over that part of its domain where it passes the horizontal line test. In this example, the inverse function looks like this. It's the inverse function that does the transforming for us. We generate a random number on 0,1, then run it through f inverse to get a new number that can model one taken from the triangular distribution shown a moment ago. Here are those steps again. Step 1, we identify the cumulative distribution function associated with the new variable we want to model. Step 2, we determine the inverse of the cumulative distribution function. Step 3, we generate a uniform 0,1 random variable, or rather, a number intended to model a uniform 0,1 random variable. Step 4, we pass the number generated in step 3 through the inverse of the cumulative distribution function to get a new number that can be used to model a random variable whose distribution function is the one identified in step 1. Before we wrap up, let's quickly see how to use uniform 0,1 numbers to generate a model for discrete random variables. Suppose this is the cumulative distribution function of the discrete random variable we're trying to model. We can find its inverse by reflecting it in the diagonal to get this. In the reflection, though, we want to swap dashed and solid lines and ultimately change the plot on the right to this. We have to do this swap because technically the function on the left isn't invertible. Notice that it fails the horizontal line test. It's swapping the dashed and horizontal lines that makes the plot on the right useful to us. We can now run random numbers between 0 and 1 through the function on the right to generate a new number taken from the discrete set x1, x2, x3. Notice that two uniform 0,1 numbers may map onto the same value of xj. Let's recap. We employed a recursion to generate a sequence of numbers that we in turn use to model an independent set of uniform 0,1 random variables. We also saw how to turn that sequence of numbers into a model for whatever random variable we liked by inverting the corresponding cumulative distribution function. You should now be able to explain how to generate random numbers, or what some might call pseudo-random numbers, on a computer. You should also be able to generate a sequence of random variables that follows a given distribution. You'll be doing yourself a favor by exploring the world of random number generation that lies beyond this video lesson. Of course, read the notes and talk to your classmates, but maybe try creating some challenging distributions of your own and simulating them. Maybe even try to convince yourself you've done things well by matching your observations with theory. Whatever you do, make sure you have fun and stay positive.